Okay, so good morning, everyone. Today we have the great pleasure to have Professor Serena Viti. She's a very good friend. And before she starts speaking, then I'm going to introduce all her achievements during her career. So Serena, she studied, she did her undergrad at Queen Mary University of London. And then she studied her PhD at University College London. There, after her PhD, then she did a first postdoc, and then straight away she got a lectureship. In 2000, I'm actually, I was checking Serena's profile, and I found that, Serena, you have an entry on Wikipedia.
No, I didn't put it
which I found amusing. So that's really great. So that gives you an idea of the importance of Serena's work in the field of astrochemistry. So she moved to Rome for a year, and that was back in 2000 and Serena?
2002.
And then she worked there as a Herschel scientist, and then after that year she went back to UCL, where she was promoted quickly to reader, and then later on to professor. And in 2016 she became the head of the astrophysics group at UCL. And recently she was awarded an ERC Advanced Grant, MOPEX, which means molecules as probes of the physics of external galaxies. And she has moved recently to the Leiden University, where she's building up a group. So Serena, we are really happy to have you here today, and the floor is yours.
Thank you, Izaskun. Thank you for the great introduction. First of all, thank you very much for inviting me to give a talk. I wish I could be there. And also I should say that they're doing some roadworks just outside the office. So apologies if you hear too much background noise. I'll try to speak loud. Okay, so today I just thought I would give a very general overview of really what I've been doing for the last few years, and in particular of the field of astrochemistry and its importance both in our own galaxy and in external galaxies. Before I move on to that, though, I'd like to present my group and to acknowledge my group, since most of the work I'm presenting here has been led by them. So just very briefly, I have half of my group is still at UCL, and then some of the members are here. So Johannes, Ross, Tom, Marcus, Matt, and Damien are PhD students at UCL, either in astronomy or in data intensive science, and John Horship and Koyu Wang are two postdocs here in Leiden, and Joshua and Luis are two new PhD students here in Leiden. So I just wanted to make sure I would acknowledge them, since there's never enough time at the end of a talk. Okay, so an outline of what I will be talking about. So since I don't know how many of you are familiar with astrochemistry, I will give a very short introduction on why we want to observe molecules in space and what we can do with molecules in the context of both our studies of our own galaxy and external galaxies. I will then move on to just give a couple of examples of recent work that we've done both in our own galaxy and in external galaxies, and I will not spend any amount of details on any of the topic, just really to give you an overview of the type of things that you can do if you observe and you model molecules in space. And if I have time, I hope I have time, I would like to just spend a couple of minutes showing you a new approach that the group has developed to interpret both the observational data and modeling data using statistical and machine learning techniques. Okay, so this is a very busy slide, so let me spend a couple of minutes, and I'd like to use this slide in a sense to introduce you on the topic of astrochemistry. Molecules essentially trace many regions in space, and especially large ranges of gas densities and gas temperatures. So if we start with the top figure there where what I call diffuse gas. So this is the gas that, of course, permeates the interstellar medium with density of about 100 to 300 per centimeter cube, and a temperature about 100 Kelvin because the UV penetrates such diffuse gas and so can heat up the gas. So in a sense where astrochemistry starts, because already at those densities and those temperatures, we can start observing relatively simple molecules. For reasons which are were not yet clearly understood, clumps, of course, within diffuse gas can collapse to form relatively stable dark clouds, and then that we can see on the left-hand side, the typical B68 dark cloud, where the densities there are higher. We're talking about 10 to the 4 per centimeter cube. And of course, the temperature has cooled down. So we are at about 10 Kelvin. And the difference in chemistry between the diffuse gas stage and the dark cloud stage is that as the density increases and the temperature decreases, of course, you have more molecules forming the gas, but also due to the temperature, atoms and molecules will tend to stick, to freeze onto the dust grains that are present in the interstellar medium. So the key two processes here between these two stages and between the dark cloud stage and the stage where stars form is that you have a collapse of the gas as well as the freeze out of atoms and molecules onto the dust grains. So the next stage, as I've already anticipated, is indeed the formation of a protostar. So if we go down, I don't know if you can see my pointer, but if we go down from the dark cloud down to the star forming course, so here, of course, your protostar is born. The densities have increased up to 10 to the 6, 10 to the 7, also 10 to the 8 per centimeter cube around the protostars. And the temperatures have increased again up to 100 to 300 Kelvin. So this means that the gas and the dust will heat up. And so whatever molecules have frozen or formed on the dust grains, they will evaporate back into the gas phase. And so you already can see that the fingerprint, the molecular fingerprint between the three different stages will be very different indeed. And of course, with protostars forming, you have jets and stellar winds, which will affect the interstellar medium via shocks, for example. And here again, the temperatures can go up by quite a few hundred of Kelvin. And so the type of chemistry and that you will see will be very different from the previous stages. And I shall not go into the stage of protoplanetary disks in this talk, but of course, that stage is also very important in terms of molecular complexity. And then somehow after your stars forms, your planets form, you will go back to some point to diffuse gas, but nobody really knows. So there is a lot of debate about how that happens. Okay, let me zoom in a little bit now onto the stages that I will talk about mainly. So I just would like to reiterate that really the key processes here when you go from diffuse clouds to dark clouds is that you have an increase in density, a decrease in temperature, which leads to atoms and molecules that freeze onto the dust. But that's not all they do. The dust will act as a catalyst, and which means that atoms and molecules can move, hop around and get together essentially much quicker than if they were in the gas phase. And so you will form complex molecules much faster than you would do in the gas phase. Every one of these stages has been observed in a molecular emission. So on the left-hand side, top here, I'm just showing you some maps of HCO+, and other species in diffuse clouds. But usually in diffuse clouds, we tend to observe simpler species because the UV penetrates and dissociates larger species. Instead, for example, in the dark cloud regime, because everything tends to freeze out, there are some key species such as N2H+, that kind of survive much longer than other species in the gas phase. And so we often use species such as N2H+, and I'm showing an example on the right-hand side there of recent observations by the Daheli and collaborators. We use some species preferentially because they tend to freeze at a later stage and much less than others. So these are just a couple of examples of molecular observations that you do if you're interested in these early stages. Equivalently, if instead you're interested in star-forming regions, jets and outflows, you would preferentially observe species that have been evaporated back into the gas phase, so they tend to be more complex. And also, as you can see from the plot here, it doesn't matter about the details, it's deliberately small, but basically in a paper by Oship and collaborators, you can see that the line profiles of these molecules is large, and this is a typical characteristics of warmer gas. Gas has been shocked. So you can also use the line width of molecular emission and not just the intensities of the molecules to determine the regions that you're looking at. So summarizing what I've just said, really, I hope I've convinced you that no matter what type of gas you look at, and no matter if it's in our own galaxy or in external galaxies, each evolutionary stage will be traced by certain molecules. Because spectroscopic characteristics, molecules will trace a large range of temperatures and densities, and you can use different transitions to trace different excitation conditions and different species and abundances to trace different gas components. So really, they can give you a very 360-degree type of picture of the gas that you're looking at. So we can observe molecules, but we need to have more tools to interpret them. In particular, we need to understand how they form in space in order to be able to properly interpret the molecular observations. So in one slide, just a little bit of chemistry. Molecules can form, of course, in the gas phase. And here the chemistry is initiated by cosmic rays, where fast hydrogen and helium nuclei will collide and ionize, and then they kind of start a chemical chain reaction in that everything else, the rest of the chemistry essentially comes from there. And in this little table here on the left-hand side, I summarize the different chemical processes that lead to molecular formation or destruction with a simple example, just to give you a feeling for what type of process go on in the gas phase. On the other hand, as I mentioned already, molecules can form on the dust grains. Here, the situation is more complex. We are not we don't understand the formation of molecules on dust grains as well as we understand the one in the gas phase. But nevertheless, as I mentioned, the dust is a catalyst, and so, or acts as a catalyst. And hence, you can have much faster formation, which leads to more complex molecules. And here is just an example of how you can get to some oxygen and carbon-bearing species on the grains from a review by Lingers and collaborators. Okay, so I hope in this 12 minutes, I've managed to convince you of the importance of astrochemistry. If you're interested in gas, that essentially is a non-stellar gas. So what I'm going to do now, I'm just going to spend the rest of the time just giving you kind of snapshots of recent work that we've been doing, just to show you examples of how you can use molecules for different aims. So in our own galaxy, we can use molecules to trace both the physics as well as the energetics. So I'm going to show you an example of physics and an example of energetics first, before I move on to talk about some recent work in external galaxy. Okay, before I start, I really like to advertise the code that has been central to all the work that I'm going to be showing you. This code is a gas grain time-dependent chemical model, so it follows the evolution of atoms and molecules in space. It's an open source code. On the right-hand side, I list the different people that have, different students and postdocs that have contributed to this code in the past, and of course also Exascom has worked on this, on a module of this code, as I will mention later. This is a very modular code and it's open source public, and that's the web address. So if you are interested in molecules, do please go and have a look at this code, which I shall not describe in any detail in this talk. Okay, so as I mentioned, I'd like to show you some results of recent studies led by Felix Priestley, who's an ex-student, an ex-PhD student at UCL, who's now doing a postdoc in Cardiff. So he was interested in understanding how you can get from a cloud, from a core, to a star, and what are the physical processes that can lead to the collapse of such core into a star. In particular, as you can see this little drawing here from the PhD thesis of Michael Horkerheid, this is a nice sketch of what happens or what we think is happening. So you have a dark cloud, you've got clumps inside the cloud, or maybe filaments now after Herschel's discoveries. These clumps will collapse into a prestellar core, and eventually you form your protostar with the disk and the outflow. And the default mode that we all assume that this is happening is via free-fall collapse. But in reality, different ideas and models of gas collapse have been proposed and have been put forward. But it's very difficult to observe this collapse as it's, of course, because at that stage the cloud is dark indeed, and it's very hard to be able to understand how the collapse is occurring. So the questions that we asked ourselves is whether chemistry can come to our aid here and can maybe be able to differentiate between the different collapse. So in other words, if you observe a molecule in a prestellar core, can the molecule gives you a hint of the history of the gas and tell you how the gas got there? Through which mode of collapse. There have been several works, several dynamical models that I list here, just examples of it that have proposed different modes of collapse. What we have done, we have parameterized the outcome, the outputs of these models into our chemical models, and then we evolved the gas from dark cloud to a prestellar core. And we looked at the results, which I will just summarize here. I will not, as I said, go into any detail, but what you're looking at here is the fractional abundances of typical tracers, molecular traces of prestellar cores as a function of the distance from the center of the core towards the envelope. And the different colors there are models run with different modes of collapse. And the key result here is that we found that there was a distinct chemical signature in some of the species between initially stable and unstable cores. And so, of course, if this were to be true, then molecules could help us understand the stability of cores that may be going into forming stars. Unfortunately, what we found, however, is that while there was indeed a distinct chemical signature, when the abundances were integrated over the column or the entire core, then these differences were much less distinct. And so in a sense, when you plot the integrated intensity, which is what you observe on the y-axis there as a function of the radius, then these differences were washed out. And so really we were left with the conclusion of we are not sure we should really worry necessarily about the modes of collapse, because at the end the chemistry seems to be settled enough that does not really have a record of the initial conditions. But you know, it's an interesting question to debate and to argue over. Okay, so let me now move on to the energetics of a galaxy. What can molecules tell us about the energetics? Well, it depends where you're looking in the galaxy. Let me take some examples from recent works that we've been doing and that involved Exaskung, most of these works, whereby we looked at outflows and jets from low mass stars. As I mentioned already, these are regions of space which are very interesting because you have this hot plasma colliding into much cooler and less dense interstellar medium, and the type of chemistry that you can get is very rich. In particular, we found from Herschel observations, which are shown here down at the bottom, that different molecules not only display, of course, various abundances, but also seem to behave differently in terms of line profile, which is telling you essentially that they seem to behave differently across the shocked region. So a classical example here is if you look at the top two spectra from the Codella and collaborators paper from 2010, you see a difference in line profile between the water and the ammonia. And this is a very intriguing problem because it's telling you something about the type of shock that we are seeing. So just there on the top, I just wanted to briefly say that there are, of course, different types of shocks in interstellar medium, but the ones that we are most preoccupied with are either J shock or C shock. J stands for jump. So a J shock is a shock where you have a sudden jump in increasing temperature and density, and then a very fast cooling. They're usually faster shocks than the C shock. C stands for continuous, and it happens if a medium is magnetized, and so the increase in temperature is much slower. The temperature doesn't increase as much, and there is a smooth cooling as well. So what can we do with this information that we get from the molecules? Well, we can run chemical and shock models, varying different parameters such as I can see from this table, the pre-shock gas density, the velocity of the shock, and these two parameters gives you information also the maximum temperature that the gas reaches. And we've used chemical modeling to interpret many observational signatures of shock, and in particular, we have used many different species. I list just some of them here, among which, of course, water and ammonia, to determine the physical characteristics and the energetics of shocked regions. Why can we do that with molecules and modeling molecules? Well, the key point is that, of course, C shocks, but in fact also J shocks affect the chemistry. So depending on the velocity of the shock, different dissociation and formation routes for different molecules can occur. And on top of that, you also have grain spattering, which, because as the shock passes, it will spatter the icy mantles, and in some cases also the grains, the core grains. And so all the materials that was on the dust will go back into the gas phase. On top of that, of course, the temperature of the gas is high, and it varies with time in relatively short time. So we're talking about hundreds of years here. And this can lead to a very rich chemistry. So let me spend a few seconds on trying to explain this complicated wiggly lines in this plot here. So what we're seeing here is 4 different shock models, which vary in gas density and velocity, and as a consequence, also temperature. And there are too many lines to concentrate your attention on, but if you just look at the ammonia line from the 2 top models and you compare it to the bottom models, you will see that as you go across the shock, so if you look at the x-axis on the second part of the x-axis, you'll see that the top 2 models do have ammonia, while the bottom 2 models do not have ammonia. On the other hand, water is present in all 4 models, and is this difference in ratio between water and ammonia in these models that allowed us to fit those observations that I was showing you before. The different behavior is due to high temperature gas phase chemistry. So essentially in the top 2 models, in the bottom two models, the ammonia survives because the temperature is not high enough to destroy it. While in the top two models, the temperature it reaches 4,000 Kelvin, that destroys ammonia via collisions with hydrogen, but does not destroy water because you need a much higher temperature to destroy water. And this simple chemical explanation can explain for you the different profiles, the different shock profiles that we see with the observations that I showed earlier. We summarized all this in a paper led by John Holship in 2017, where we also released a public version of our model. And so this is a BC table, but I think it's very telling because on the y-axis you have, so basically this is a collection of results from a large grid of models, where on the y-axis we varied the gas density, on the x-axis we varied the velocity of a shock, and then at the top of each box is the maximum temperature reached by the shock, and then in the box you'll see a collection of molecules color-coded, where the species in red are enhanced initially by the shock, but are then destroyed by the shock as the temperature increases. The species in bold are those with which exhibit a given behavior, but only for a small range of conditions. So then this makes this particular molecules very interesting, because not only they trace a shock, but by tracing only particular type of shocks, they can actually tell you a lot about the conditions. The ones in blue are instead the ones that are enhanced by the shock and trace its full extent. So they're interesting because they tell you there is a shock, but it's not actually telling you much about the shock conditions. So far I've talked about C shock, but in fact, as I mentioned earlier, there is also the possibility that a lot of the gas that we see in these outflows is dominated by J-type shocks. So we were interested in trying to understand the differences chemically, if there are any, between J and C-type shocks. So this is work that's been led by Thomas James, and he devised a kind of a parameter to determine the differences in chemical signature between these two shocks, but without going into details about these parameters, suffices to say that if you look at a box like the one I'm showing you for methanol and water, and the color is quite uniform, it means that this particular molecule is not a good tracer to differentiate between the two types of shocks. This can be seen also in the more traditional type of plots, where the abundances are plotted as a function of as the shock propagates. And so we looked at different molecules, SO, SO2, HCN, and ultimately the conclusions that we got from these colorful plots is that there are some differences between J and C-type shocks from a chemical point of view, but the largest difference are results of different sputtering and evaporation behavior, which happens between shock types at low velocities and low gas densities. In other words, when the shocks are fast, you cannot really differentiate the chemical signature between C-type shocks and J-type shocks. Okay, so in the last 15 minutes or so, let me move on to describe some of the work we've done in external galaxies. Here, of course, things are much more speculative. And the reason for that, I will show you the reason for that in a minute. But before I move on, let me just put astrochemistry in external galaxies into a bigger picture, into a larger context. There are many questions that extragalactic observers ask themselves. I picked 4 because these are the 4 where I think astrochemistry can actually help. We have studied star formation in our own galaxies for decades now. There is no reason now, with the sensitivity of so many instruments, that we cannot understand, or we cannot study star formation in other galaxies as well. So we are interested in understanding what physical processes drive star formation in galaxies. We know that galaxies all have an active galactic nucleus. Some AGNs are more dormant than others, but nevertheless, one of the key questions that we still don't understand fully is how AGN are fueled. We know that IGN must affect the surrounding interstellar medium, but whether they quench star formation or they help star formation is still an open question. So we're interested in understanding how AGNs affect the surrounding interstellar medium. And in general, we also know that galaxies sometimes merge and interact with intergalactic medium, and the type of processes that go on there are very nice processes for astrochemistry to investigate. Once I put extragalactic astrochemistry into the context, let me go back to the reason why I think it's very different to study extragalactic astrochemistry than galactic astrochemistry. The differences comes mainly by two challenges. The first one is that even when you look at the closest galaxies, the spatial resolution, even the highest spatial resolution that you get with ALMA will encompass a few parsecs of gas at least. This means that the molecular line emission that you see is a signature of multi-phase interstellar medium. So you have different gas components and possibly different temporal effects all diluted into your beam. So you're in a sense, you're blind to individual processes. This is a challenge I will mainly concentrate on for the rest of the talk, but there's a second challenge, of course, which is the fact that now in nearby galaxies, the spectra are proving to be as rich as the ones that we see in the Milky Way. So this is a beautiful preview of a spectrum from the ALMA large program Alchemy, and this is from a paper in preparation by Sergio Martin, who's leading this, from a European side, is leading this large program. And I think it's obvious from the spectrum that the spectrum is complex. There are a lot of molecules there, and the line identification is very complex. But we shall not talk about this in this talk. Okay, so let me then start by, oops, sorry. Let me just start by talk about what we want to do with astrochemistry and extragalactic astrochemistry. What we want to do with astrochemistry and extragalactic science. So the main question here is that we want to find key molecular transitions that can trace the individual physical and energetic processes that go on in our beam. So as I mentioned, the beam will be an ensemble of physical and energetic processes, and we like to find key molecular transitions that can disentangle and basically make us unblind to this ensemble. To give you an example that has been used a lot, HCN and HCO plus are used a lot as tracers of, let me see if I can find my cursor without clicking on anything I shouldn't be clicking. Okay, yes. So HCN over HCO plus, it's a ratio that's been used a lot to study and to understand the energetic in galaxies. And in particular, it's been found, for example, in the antenna galaxies, in the nucleus, in the nuclei of the antenna galaxies, as well as in the nucleus of NGC 1068, which is on the left-hand side, to be higher, enhanced compared to the overlap region of the antenna galaxies or the starburst ring of NGC 1068. So often a statement that is made or a question that is asked is this higher ratio a hint of high excitation, or in other words, is an enhanced HCN over HCO plus a sign of AGN activity? And my answer to that is that, well, not so fast, because several studies are showing no enhancement of HCN over HCO plus at all in AGN. Here, for example, you have a plot of NGC 3256 in this ratio by Arad and collaborators that really is showing that this ratio is not varying at all across this across galaxy there. And more recent work that we've done, led by George Priven, we actually we looked at a sample of galaxies with strong AGNs, and we did a statistical correlation between the ratio of HCN over HCO plus versus the luminosity of AGN over the infrared luminosity. And essentially, statistically, we could not find a strong correlation. This is in a sense backed up by theoretical work we've been doing. If you look at the left of the right-hand side here, this is the ratio for different transitions. So the 1 to 0, 2 to 1, 3:2 of HCN or HCO plus as a function of time for many chemical models where we vary both the cosmic ionization rate and the density. And as you can see from the y-axis, without going into the details, you can see that this ratio varies a lot. And it's very hard to pinpoint the variation to just the presence of the AGN. This is more obvious maybe by what I call my chaos plot, which is the one on the top there. And what you're seeing a bunch of blobs. And so this is the ratio again from HCN to HCO plus for 4 different lines from 1 to 0 to 4 to 3. So 1 to 0 here, 4 to 3, as a function of the different models that I've run, and I've run them for a large range of densities, temperatures, cosmic rays, and radiation fields. And you can see that the dots, this square cover the whole plot. Essentially, the message here is that very different chemical models can give you very similar line intensity ratios and vice versa. So what can we do about it then? Can we solve this problem? And the answer, I think it's yes, but we need to have a very systematic methodology. So we can't just take a ratio. We need to obtain multi-lines, multi-species observations at the same spatial resolution and apply parallel analytical tools, parallel analysis tools from LTE down to chemical modeling and combine them in order to interpret the observations. And so what I'm going to show you now is an example of this particular methodology applied to the composite galaxies NGC 1068, which is an AGN plus a starburst galaxy. So it's got an AGN which seems to be powerful, as well as a starburst ring. So it's a beautiful extragalactic laboratory for us. And this work has been done in collaboration with many people, which I list on the right. And there are also many other groups apart from ours that are working on these galaxies, which I hope I've gave credit to with some of the references at the bottom. So just to recap, the strategy here is to observe as many molecules as you can with as many lines as you can at the same resolution, and to apply a fairly complex model to interpret the observations. So let's start by looking at CS. CS is it's a long-standing, has a long history as a very nice high-density molecular tracer, both for our own galaxies and in external galaxies. And here is a paper led by Matt Schofield, a PhD student at UCL, where he combined 4 transitions of CS, both in the circumnuclear disk here of a galaxy as well as in the starburst ring, and analyzed the data. I don't have a time to go into it, so I'm just going to give you the results of this data, which show in this plot. And basically, the bottom line is that CS is everywhere, so cannot be used just to identify a particular region, AGN or starburst. On the other hand, we found that the 3:2 line seemed to be particularly stronger in the starburst rings than in the circumnuclear disk. We also used this different information that we gathered from all the spectra and from our model to draw this little drawing here. So what Matt did here, he did a map of temperature, a map of gas density, and most importantly, something that you don't usually get, or you can't get from radiative transfer alone, a map of cosmic ionization rate across the galaxy. So in the center, so that the cross in the center is the CND, and then on the top and bottom, you have the spots that we observed in the starburst galaxies. And so as you can see, there is a trend in both temperature, gas density, and cosmic rays. And we could do this just with CS, but we needed many lines. Moving on to different molecules, SIO and HNCO in this case, we chose them because they are very interesting molecules to trace shocks. They're different in that SIO is released mainly from the dust grains due to shock sputtering of the core grains, while HNCO will form on the surface of the dust grains and can be released in the gas phase by either slow shocks or simply warm temp, as long as the temperature is above 100K or so, it can be released. So we had some observations of SIO and HNCO. Unfortunately, not many lines at the stage when we did this paper, led by Kelly and collaborators in 2017, who was a student at UCL. What we found, again here, I won't go into any details, but we found that SIO and HNCO were almost anti-correlated, with SIO peaking on the east part of the AGN, while with HNCO peaking in the west part of the AGN. And we nicely could explain this with two different shock models. If you look at the top plot, top left, and you concentrate on the blue and the red line, you see that the blue line, which is the SIO abundance, is much higher than the red line, which is the HNCO abundance. And that is a fast shock. The bottom plot instead is representing a slow shock. And here you can see that the red and blue line are swapped. So HNCO becomes more abundant in slow shocks than SIO. So our conclusion here was that the east part of the AGN seems to be much more shocked than the east-north part of the AGN is much more shocked than the west part of the AGN. And interestingly, this seems to coincide with the direction of a motion of an outflow that is driven by the AGN. This needs to be confirmed, so we obtained many more transitions of HNCO and SIO, and so far preliminary analysis led by Wang and collaborators is confirming this picture. Moving on to another interesting molecule, C2H. We also observed C2H in the, along the AGN and the outflow of NGC 1068, and we found an interesting and surprising result. We found that this molecule is very extended and seems to trace kind of the edges of the outflows. And most importantly, first of all, I should say we only had one line. Okay, so obviously one line is extremely difficult to draw any strong conclusion, but nevertheless, because of the hyperfine structure, we could determine that the gas was in LT in this particular molecule. And so we could determine the column density of the molecule by assuming a range of temperatures. And no matter what temperature we assumed, the abundance of the species was always very high. So if you look at the table there, even for 10 Kelvin, and we know that the gas is not at 10 Kelvin, the abundance was 10 to the minus 8, which is the highest abundance of C2H found in diffuse gas in our own galaxy, and it only tends to decrease when you move to dense gas. So we really could not find a good explanation for the high abundances along the outflow of 10 to the minus 6, 10 to the minus 7. And so we applied our modeling methodology, and the only models that seemed to be able to reproduce such high abundance of C2H were if you have a turbulent, very thin interface of dense material, which seems to be consistent with the fact that we saw C2H at the edges and along the outflow. So we think the C2H is tracing, for the first time in an external galaxy, the turbulent interface between the outflow and the interstellar medium from the AGN outward. We are now looking at C2H in multiple lines in different galaxies in NGC 253. This again was part of the ALMA Large program led by John Holship, and is in preparation, but I just wanted to show you the maps of these 4 lines of C2H in NGC 253, which actually are telling us a different picture for this particular galaxy. And it's interesting because the difference between NGC 253 and NGC 1068 is that NGC 253 is kind of a pure starburst, so it's dominated by starburst, while NGC 1068 has got a strong AGN. Okay, let me finish now in the last 2 minutes to completely change the subject and advertise a little bit the work that a lot of members of my group have been involved recently, which is basically to try to devise as the problems are becoming more complex, to try to devise statistical and machine learning tools to aid the interpretation of molecular observations. As a little intro to the problem, in astrostatistics, in a sense, you can define 2 types of problems: the forward problem and the the inverse problem. So the forward problem is basically you have a theoretical model that is formulated a priori and relates or maps the model parameters with observed data. So an example in astronomy, in particular in astrochemistry, if you look at, again, this dark cloud here, you're predicting the molecular abundances from the gas given a physical parameters for the cloud. So you have a physics for the cloud and you're predicting the molecular abundances. And this is a forward problem. An inverse problem is the inference of model parameters from the observed data. So again, applied to our example. So this is the outflow that I've shown you already at 11:57. So here we are given molecular abundances from the observations, and we are inferring the physical parameters from this observation. And so this is a typical inverse problem. I don't have the time to go into the details of why we are faced with these problems in astrochemistry, but I would like just to advertise, in a sense, works that we've been doing for both of these type of problems in the past and that we're doing at the moment. So the first two categories here, we have used Bayesian inferences to understand to understand the microscopic problems in astrochemistry. In particular, I mentioned at the beginning of the talk that we don't understand well how molecules form on ices, although there are many experiments that people have been doing across labs across the world to understand interstellar ices. It's very difficult to do these experiments because it can take months to just analyze one reaction under only very specific conditions. So it's almost impossible to do experiments for every molecule that we know forms on the grains. So we have been using Bayesian approaches to try to understand that. And so this is for more the galactic side of the work. From an extragalactic point of view, I mentioned that of course, we're working at larger scales, larger beams, and many people really are not interested necessarily in individual star-forming cores, of course, in external galaxies, but they're interested in the dynamics of the galaxy. And so they would like to understand the chemistry in the context of dynamical models. And this is often difficult because coupling hydrodynamical models with chemistry is a very difficult problem. So we've been working on essentially trying to bypass the chemistry and to build up both chemical and radiative transfer emulators. And so this is the work here led by the Jolla and also Horship. All this work, we are now trying to put it into a very interactive, user-friendly, web-based modeling tool. This is work led by Largescale. And basically what he's doing is essentially putting everything I've been telling you about, I've been talking to you about, into one mega tool, very user-friendly, which involves both chemical modeling, radiative transfer, but also emulators based on machine learning techniques. So let me now conclude here. I guess I got 4 messages really, which I hope I managed to transmit during this talk. The first one is really that when you want to do astrochemistry, whether in our own galaxy or in other galaxies, you do need to look at different species and also at different transitions, because they will give you a different view of the gas that you're seeing. Often in external galaxies or in studies of external galaxies, people tend to get attached to a particular molecular ratio and hoping that they can use the ratio as a unique tracer. And that's really not the case. You need multiple ratios in order to trace the dynamics and the chemistry and the physics of a galaxy. I hope I also convinced you that sometimes it's not enough to stop at LTE or radiative transfer analysis, but that you need chemical models so that you understand the chemistry behind the molecules that you observe. And finally, in an era where we are submerged by observational data and we can do millions of models very quickly, we really need to move on to statistical and machine learning techniques and methodologies which have been used by our cosmology colleagues for decades already to solve some of the problems that we have faced. And I leave you with my financial acknowledgement and thank you for listening.
Thank you very much, Serena, for this very nice talk. So are there...
Can I stop sharing?
No, leave it there. Right. Just in case maybe there's any question that requires going to one particular slide. So are there any questions? Oh, and then I'm going to start. So I found very interesting the models where you have been comparing the different physical models for the collapse of starless cores. And then, so I was wondering, I didn't catch very much the numbers, but I was wondering whether the differences that you see could be tested by performing large scale maps of these starless cores instead of single pointing observations.
Yes, that's a very good question. Obviously, I went through quite quickly. The answer is that is yes, I think. At the moment, we found it hard when comparing to the observations that we had at hand, from the literature, while the fractional abundances seem to differ quite a lot when integrated across the core, these differences were essentially smoothed. And so we were not too optimistic with the observations at hand at the moment. But indeed, I think mapping the whole core up to when it's not bound anymore could be a way. The problem, however, with it is that even the dynamical simulations, so not just our codes, but even the dynamical, the MHD simulations, when you start going towards the envelope, they're not as accurate as the simulations closer to the core. Okay. So there are a lot of uncertainties, but certainly I think observationally, yes, you're correct that mapping, more extended maps should help. It would be very, very nice to be able to differentiate between modes of collapse.
Yes, that would be really, really interesting. Okay, so maybe we need to talk then later. Yeah. We have large scale maps, so maybe we can use it.
Great.
Okay, are there any other questions from the audience? No. Yes, please, Jesus, go ahead. You need to unmute your microphone.
Yeah, thank you. Well, thank you very much for the nice talk, although I was able only to listen to you in the last 30 minutes. Sorry, I was in another telecom. I've seen one of your points that I think it's a critical one is that sometimes or very often we have degeneracies that we cannot really uniquely point out molecules to trace a given process. So my question, I hope that we have a couple of them or three. You show some cases which clearly seems to break the degeneracies. But in general, my question is a general question which is related to all the tools that you're developing. Do you think that all the information we get from ALMA, which is a huge amount of information, will really help us to really break degeneracies?
Yes, I do actually. I think our problem at the moment is just what you said, that we have this enormous amount of information, but it's all in pieces. And none of us has been able yet, for obvious reasons of time and also vision, to put all these pieces together into one big collage, in a sense. So we end up, looking at different spots in different galaxies, in different molecules, and then we extrapolate from this information, the gas density, the temperature, and then we speculate on the origin of this gas density and of this temperature. But we haven't yet, and I'm hoping to do that. It's part of what I would like to do with my ERC, to put together all these pieces into one coherent picture, where we stop by looking, by just looking at a spot and being blind about the rest. And I think a key point here is that we need to introduce and to make sure that those who are worried about the kinematics and the dynamics talk with those of us who are worried about the chemistry. And in extragalactic works, this does not very often happen. And I think we need to, in order to look at the big picture and also to break some of the degeneracies. I think we're already doing it by looking at many, many molecules, but I agree that until we concentrate on only bits and pieces, this is not so easy.
What would be the best strategy in terms of selection of objects and type of observations?
Yeah, so that's the other problem, I guess. That again, unlike the galactic counterpart in external galaxies, at least so far, it's been quite hard to ask to do large surveys of objects in many molecules, right? I mean, it's for obvious reasons, it's a lot of time. But ultimately, this is really what is needed. I mean, if you look at, for example, those who do, those of you that do surveys of CO in a sample of galaxies, like what is it called, the cold mass survey from IRAP, for example, or the one from the JCMT, and you collate many informations from many lines of CO for many galaxies, that's already really helping you to connect the large scale with the small scale and to break some of the degeneracies there. Of course, CO is much easier to observe than any of the molecules that I've been talking about. And so I think in terms of strategy, I'm afraid we will need to go into a small sample, but little surveys of more than just one galaxy. So at the moment, all my work, for example, has been concentrated, or most of my work, on NGC 1068 or NGC 253. And they're great astrochemical laboratory to try for us to get trained. But so it's almost like, we've been trained on these two galaxies, but now it's time that we get out of in the world and look at more galaxies.
Okay, well, I have another, this is a detailed question. I mean, you showed beautiful results in C2H, and you said it's basically looking into the working surface of the jet.
That's a speculation because we only had one line, but yes.
Because my question is then, what did you see in the starburst ring? Did you see some enhancements of C2H also?
So in the starburst ring, it's there, but the abundance is more consistent with what you would find in diffuse gas, like in our own galaxy. The thing is that when instead, so it was about 10 to minus 8, again, with one line, assuming LT, etc. So a lot of caveats there. But so there it was abundant, but in a sense, because of the strong UV radiation of the starburst, we could justify that abundance. But it was along the outflow that was really much more abundant, between 10 to the minus 7 and 10 to the minus 6, depending on what temperature we assumed. And that type of abundances are very hard to make with chemistry, basically. And the only chemical model that could do it was the model of a turbulent interface, or in other words, you could only maintain that high abundance for a short period of time, and that's why we invoked episodic turbulence. That's why.
So it's basically low velocity shocks, what you are implying then.
So, sorry, say it again?
This is basically low velocity shocks.
That's right, and episodic and constant in a sense. While in NGC 253, we haven't published it yet, but in NGC 253, what we seem to be seeing instead is more of typical of kind of starburst regions, which kind of makes sense because the AGN there is not, that maybe there isn't a powerful outflow as there is in NGC 1068, but I don't want to really say more about that because we're still finalizing the analysis of the data for NGC 253. And there, of course, we've got 4 lines, so it's much easier to draw conclusions, or at least to believe our own conclusions.
Mm-hmm. Okay, thank you, Serena. Thank you very much for the nice talk.
Thank you. Are there any other questions? No more questions. Okay, well, thank you very much, Serena, for joining us today. And before we finish, I would like to say that for the participants, so if you need an attendance certificate, please contact us at the email address at seminarios@CAP, etc. And please send us an email with your information, and then we will prepare the attendance certificates for you. So Serena, thank you very much for joining.
Thank you.
Thank you very much to everyone, and see you next week.